All right, thank you very much, Amanda. After I wrote the, first of all, I should explain, I've been asked to combine two talks, hence the cumbersome title. After I submitted the abstracts, the LPI hosted 9 graduate students who have helped fill in a lot of the gaps. So you can see that there's a large number of additional names on this now. And we're going to be presenting some evidence that is not in the abstract. This is a little risky in science. But I told the graduate students that if we're going to meet a 5-year schedule, we're going to have to break down some barriers and share some information a little bit more quickly. So we're going to do that today, okay? All right, so I need to introduce the South Pole to you. It's located on the rim of Shackleton Crater. In this map perspective, the near side is towards the top, the far side is to the bottom. Shackleton Crater itself is about 21 kilometers in diameter. It's similar in size to central Houston, and it's 3 times deeper than the Grand Canyon. It's a pretty immense structure. And that's one of the important things that everybody has to get in their head. The South Pole is a topographically extraordinary place, which is kind of neat, but it also poses some challenges. Okay, so the other thing to point out is it's a heavily cratered terrain. It's not marry in any way, shape, or form. It sits on the margin of the oldest basin, the South Pole Achan Basin, which is 2,500 kilometers across. In the immediate vicinity of Shackleton, that pointer's not going to work. You can see a variety of other craters in this geologic map produced by Spudis and all. De Gerlach and Haworth are among the oldest craters in that region. Shoemaker and Faustini may be a little bit younger, although that is an issue that is in debate in the community. Shackleton, it's important to understand, was produced after the basin-forming epoch, which, if you're talking about volatiles, is important, as I'll go into in a moment. As I said before, this is an area that has dramatic topography, which is very important when you're discussing ops issues. There are very long shadows and very deep shadows. And in stark contrast, a few small, nearly constantly illuminated sites. This is a map that NASA's released about a month ago that illustrates 4 of them that they're looking at. 2 of them are very close to Shackleton Crater. One is on the rim of De Gerlach, and one is what I will say is in the lower right quadrant of the pole. You can't say southeast, southwest in this polar configuration, as everything is north from the pole. So it's a little bit confusing to talk about. We're going to spend most of our time today looking in the vicinity of sites 2 and 3 there. So you have these highly illuminated areas, but next to them, or juxtaposed next to them, are these PSRs. These can be traps for volatiles, as Carly Peters mentioned, providing a scientifically rich library of the delivery and evolution of both internal and externally delivered volatiles throughout solar system history, while also providing potential in situ resources. Okay, so this is how we traditionally look at the distribution of volatiles in the polar region. These are volatile stability maps. In this particular case, it's for water. It also shows a landing site that we have proposed in the past. It's not at the South Pole, not on the rim of Shackleton, but in a flatter plane below the rim of Shackleton. But I'm going to suggest that we need to look at this a little bit differently as we move forward in an ops perspective. That is, we have to think in terms of geologic evolution, okay? Understanding volatile sources as the moon evolved is important because that constrains when and thus where the volatiles were deposited. That, in turn, constrains the chemistry of any ices, which will greatly affect ops associated with in situ study of them. For example, volcanic and potentially impact source volatiles may contain abundant sulfur. That was actually seen in the L-Cross experiment, which may produce corrosives during ISRU ops. Okay, so I want to focus on just 2 of these here briefly. One, volatile surface delivered by impacting asteroids and comets during the basin-forming epoch. And here I've plotted the log of projectile mass that produced the basins during the basin-forming epoch as a function of time from 4.4 to 3.7 billion years ago. And first of all, one of the punchlines is, which everybody knows, a tremendous amount of mass was delivered to the lunar surface. The other thing, though, to keep in mind relative to the South Pole exploration is that not all of the craters that we see in front of us at those landing sites were always there. Haworth and de Gerlach may have been able to sample most of the volatiles, except for the South Pole Achan Basin delivered ones. Shoemaker and Faustini only were collecting the end of the basin-forming epoch volatiles, and Shackleton wasn't there at all to collect those volatiles, okay? So let's look at another important source, indigenous source, vented volcanically from the lunar interior. This is some work that Deborah Needham did a few years ago. Here is a plot in the lower left of mass volatiles, carbon monoxide, sulfur, hydrogen, and water equivalent. There was a large pulse around 3.8 billion years ago. There was another pulse at 3.5 billion years ago, and then a little bit dribs and drabs of volatiles vented at younger periods in time. Volatiles were potentially these volcanic volatiles were potentially trapped in Haworth, de Gerlach, Shoemaker, and Faustini, but again, not in Shackleton. The last of the volatiles may have been trapped in Shackleton, but by and large, no. Okay, so that type of geologic evolution of craters and in the South Polar region would have produced a stratigraphy of different volatile abundances, as well as variable lateral abundances and depositional units with different compositions. All of that is going to be affecting ISRU ops. Okay, now I've been talking about large PSRs, if it wasn't explicitly stated. Let's spend a moment talking about small PSRs that may exist around the rim. The South Pole is, again, this thing's not going to work exactly like I want it to. No, okay. But there's a little cluster of what may be little PSRs right at the South Pole. There's some other ones on this ridge and down in the plains below the South Pole. And there may be some small PSRs cast by boulders along the rim, and I'll show you an example of that in just a moment. These are suitable sites for sampling potentially volatile, richer regolith in special environmental containers, just like we did in Apollo, although these are not going to be sourcing the volcanically vented materials and basin-delivered materials because these are going to be much younger features. This is the South Pole, and there's some deep depressions in the vicinity of that, so there may be some PSRs within walking distance of the South Pole, if in fact we land precisely at the South Pole. Again, but these are going to be dominated by solar wind volatiles. This is a map that was put together by Matt Ziegler a few years ago, illustrating the depth at which volatiles might be stable. The reds are at the surface, blues that you see there are about 2.5 meters beneath the surface, and there are a few places along the rim and this ridge here in the lower left quadrant from Shackleton that may provide access to volatiles. A field geologist is going to want to trench. It's really the best way to understand the distribution of volatiles because there is going to be, in the lunar regolith environment, lateral variations that you want to understand. The technologists, of course, always want to drill, and in both cases, you probably want to have mass spectrometers available to you to do some in situ analyses. I think it's also important to survey the subsurface as opposed to just taking point measurements. And a good way to do that is putting ground penetrating radar and neutron spectrometers on every bloody rover we send up there, including the crew rover. These surveys could be conducted with a small robotic rover or with the crew rover, including telerobotically between crew missions to the surface. Okay. Now let's shift to geology. I've been talking about volatiles, which is related to ISRU. There are rock samples, yay. The geologists are going to be happy. The most accessible samples will be Shackleton Ejecta, however. We're not going to have the spectacular outcrops that we have, for example, in the Schrodinger Basin, which I've spoken about oftentimes in the past. Potentially, this impact ejecta will include Shackleton impact melts for which an age can be determined. The regolith may also contain impact melt from the South Pole Achan Basin, other pre-Nectarian and Nectarian age impacts, fragments of the original highland crust, and I will show you an example of that in just a moment. Okay, so here's an example of some of the material that can be accessible to crew during EVA. This is near the rim of Shackleton Crater, and this is an immense rock exposure. And this is just one of many. This is over 100 meters of rock exposure. And that's really important. Think about that for those of you who have driven on American highways once that highway system was built. There were all these beautiful road cuts that expose the subsurface, and geologists and geology students just love those because they can infer some geologic context from them. Well, these exposures are so large, you are going to be able to get or extract a similar level of geologic context. There's a variety of boulders of all sizes around the rim. There's additional outcrops or boulder exposures, and some of them are producing small PSRs. Thank you, Amanda. And so these can be sampled much like we did in Apollo 16 and 17. Many people, I think, forget, but PSRs were noted during Apollo and samples were collected. Okay, now, we do have some additional data of the Shackleton area provided in part by Kaguya. And all these red squares are places where in 500 by 500 meter pixel sizes, we have spectra of pure anorthosite identified. The students have been very good about zeroing in on using NAC imaging and identifying these actually in the crater walls. And so here we have a beautiful exposure of pure anorthosite sitting here in the basin wall, and there may be more. We know this is pan because it is keyed directly to a return spectra. That's probably pure anorthosite there. And so the crater was cutting through and excavating pure anorthosite. That means some of those bright white boulders I was showing you earlier are going to be pure anorthosite, which will be very exciting. Now, most of the pure anorthosite in around Shackleton is located near the South Pole and approaching the ridge. If you look at the crater wall where the crater intersects that ridge, the geology looks different. We haven't been able to discern what that geology is, but there does seem to be some heterogeneity in the crater wall. Moreover, if you go around to the far side of Shackleton Crater from the South Pole, you see something different yet again. You see that the upper 200, 250 meters is composed of a layered terrain, something we've not seen before. This is, I'm going to zoom in on it. This is composed of layers that are tens of meters thick, forming a total sequence of 200 to 250 meters. These are probably impact ejecta units from older impact craters cut through by the formation of Shackleton Crater. We've put together an ice sail simulated model that shows the formation of Shackleton Crater. That confirms our observations that there should be about 150 meters of Shackleton ejecta on the rim, and we are actually now mapping that to see what part of the area around Shackleton may have been covered by Shackleton ejecta. If you are going EVA, and I know I'm running really close on time, yes, so I'm going to go through these last couple of slides really quick. Topography, again, is really arduous. So if we were to land at the South Pole and ask crew without a mobility unit to walk, say, 2 kilometers, they're going to have to go upslope 140 meters. That's a bit of a struggle in a spacesuit. If they want to go to this ridge, which looked very comfortable in some of the lower resolution images, they're going to have to go 500 or 600 meters. In a spacesuit, probably not. So some type of mobility asset would be nice. We've tested unpressurized and pressurized vehicles in the past. It would be great if these were pre-deployed, and I heard that. Literally, I am finishing up here with this slide. So if you put those robotic assets on the rim of Shackleton, they obviously will be of some great use on the rim. The problem is getting them down to explore a broader region, because that rim is 1 kilometer above the surrounding plain, and the slopes there in yellow and green are untrafficable. And so that's going to be a challenge. There are a couple of solutions. I don't have time to get into it because Amanda won't let me, but yeah, it will be a challenge. Thank you very much.
Great, thank you. Who has questions?
Hi, Barbara Cohen, NASA Goddard. Hey, Dave, when you talk about Shackleton ejecta, of course, that's could be a window into what was under Shackleton. Mm-hmm. What was under Shackleton? What did it eject?
Oh, well, that's why we were looking at the walls of Shackleton. For sure, it looks like it excavated this pure anorthosite, assuming the spectra is correct. It excavated ejecta from older craters. Maybe that's ejecta from Faustini. Maybe that's ejecta from Shoemaker. It is, as I said, towards the beginning of the talk, right on the edge of the South Pole Achan Basin. So some of that material is either excavated from the South Pole Achan Basin or potentially uplifted. We're right on the edge where there is a series of massifs. Ben Busty is standing right behind you. He was one of the co-authors on that Sputus et al. Paper that mapped many of those units as massifs, which was one of the reasons we started taking a look at the intersection of the crater wall with that ridge, which may effectively be one of the South Pole Achan massifs.
What data do we need to distinguish what those materials are?
The best data is to put well-trained crew down on the ground and collect samples and bring them back for you and me to analyze.
But we do have remote sensing data, but the M-cube data isn't that good at the South Polar regions, is that right?
That is correct. Yeah, we do not have good M-cube data, and Carly can explain that.
Yeah, oh man.
Yeah.
We need another cycle, yes. One of the issues you raised in your talk, which I found fascinating, is the stratigraphy at the South Pole. And in particular, that Shackleton is one of the most recent events. And it's been the focus for much of the discussion. But if we want to get a stratigraphy of deposits over time, the interior of Shackleton is clearly not the place to go. Have you or your group tried to do what was the South Pole before Shackleton to reevaluate the permanently shadowed areas that may be accumulating a time variation of the volatiles?
Yeah, Carly, that's kind of work in progress. You were at Manchester, so you know I started that process there. The students were going to help me look at that issue in Faustini, Shoemaker, and Haworth, but the geology of Shackleton itself was so interesting that we just collapsed our focus on that for the summer.
Okay, great.